yeah, it is. God, it goes fast, doesn't it?
Did you do a lip project?
What?
Did you do a lip
Oh yeah, I did it in the first 2 weeks.
Me never.
I've got a third year mate. Oh, he just graduated. He graduated last year, and he was like, "Do it now because you don't have time later."
I'll check
Done. I've got like 1,000 more words to do maybe.
take my part.
You've not started it, have you? You've not started it, have you?
I've done like, I read a few articles.
So no.
Oh no, I need to do it.
Quiet, please. Morning. You're excited at 9 o'clock? Right, last time I left you a question to look at in the few days since last lecture. And what I asked you about was we add sodium to liquid ammonia, it goes deep blue. And if you add benzene with an alcohol, we end up making the unconjugated cyclohexadiene. Do you know what reaction is called? Birch reduction. Birch was a head of school here in the late 1960s. Birch reduction. This is a fast example of a radical reaction. And sodium, being what it is, likes to become sodium once plus. If we put it in water, we make sodium hydroxide and hydrogen. That becomes sodium once plus. Put it in ammonia, we don't generate hydrogen. So in ammonia, we get sodium once plus, and what are called solvated electrons, which don't reduce the ammonia. And those solvated electrons swimming around in ammonia give us this real deep blue colour. So basically we've got a source of electrons. Benzene, of course, is a highly conjugated system. And we can give an electron to benzene to make a radical, or radical anion. And that is the first step of the Birch reduction. So formally, if you think about benzene as being 3 double bonds, you can take one electron and pair it up with our electron from our sodium, and we put one electron onto the adjacent carbon. That is a one electron reduction of an aromatic system to give a radical anion. So an extra electron in the pi system. Radical anion. That of course has got lots of resonance forms, but it's also very, very basic. So I'd like to pick up a proton. Who knows what the pKa of ammonia is? Where's my kitchen tool? It's 35. This is basic enough to deprotonate ammonia. To give NH2 minus. So we make sodium amide overall. And a single radical species. Right, radicals are highly reactive. As we know, reactive intermediates. We've still got blue ammonia with electrons in it. We can give that radical a second electron. And that gives us an anion, so-called pentadiene anion. So we're now into anionic chemistry. That of course has resonance forms, 2 degenerate ones and 1 not. We draw the non-degenerate resonance. that. And of course, there's a third resonance which is identical to the first one. That, of course, is also basic, but it will deprotonate something much more acidic, such as terbutanol. And you only protonate the central anion. I'm not going to tell why, we haven't discussed the relevant orbital theory as yet, but that is where the highest electron density is, on that central carbon, and that's what we protonate to give us the unconjugated cyclohexadiene. It's a Birch reduction. Very nice way of making what appears to be not thermodynamic products. You'd expect the conjugated diene to be thermodynamic, but we've got the non-conjugated one. Classic Birch reduction. They first carried out in this department. Okay, I've got some more questions which I'll hand out at the end the next time. We've got the right amount of sodium in there. Of course, the reaction will lose its blue colour at the end if you consumed all the electrons. Right, so that's the Birch reduction. Right, last time we're just finishing off my first sheet, and I was going to tell you, or show you a few examples of nice radical reactions that we're going to meet again later on, just to show you the power of free radical chemistry in terms of synthesis. So, we'll got your sheets from last time. Media services apologise for the lack of vision over that side. Apparently there's something missing in the projector. Seems to be common for this lecture course. Right, so these are a few examples of the sorts of things we can do with radicals. That's a steroid. A ring system like that is called a steroidal skeleton. And the first thing we do when we're thinking about radical reactions is we look for weak bonds. And there's a particularly weak bond in that molecule, and that's the ON bond. We're talking about homolytic processes, so we're looking for weak bonds always to start a reaction off. And usually at the end of the day, we want to make a strong bond to compensate. UV light, of course, is very energetic, and under UV light conditions we can break that bond. And we'll discuss the full mechanism of this in a week or so's time. But the product from this reaction is quite impressive. Because we functionalise what appears to be a completely unreactive centre, and that's that methyl group. So the nitrogen from our nitrite is ultimately transferred to that methyl group, and we generate a new functional group. As I say, I'll go through that in detail in lecture 4. You couldn't do that any other way. There's no way you can functionalise that methyl group. It's a saturated carbon, completely unreactive. And what we generate to compensate for our loss of the ON bond, we generate a nice strong bond, an OH bond. So this idea of breaking weak bonds and forming strong ones is ultimately at the heart of radical chemistry. So if you look on Blackboard, I've given you a summarised list of bond strengths. You don't need to learn them, but you need to have a feel for relative strengths. I'm just going to show you that bond is 230 kilojoules per mole. That's what we call a weak bond, 230 kilojoules per mole. We're making an OH bond. That's a strong bond. That's 414. So what you'll find is radical chemistry is very logical. You look for weak bonds and make strong ones. And we can use that very nicely to otherwise radical reactions. And that, of course, is a oxime we've generated on that carbon. That's called a remote functionalisation, because you're functionalising remotely from what appears to be a reactive position. Okay, so that's not a carbon-carbon bond forming reaction, but it's a functionalisation. The most powerful use of radicals is to make carbon-carbon bonds. And again, we'll look at this in much more detail, but this combination of reagents, I'll explain again later on, is a way of forming radicals. Just remember my little ester there. Again, you look at your starting materials and there is one bond that is weak. And that's the carbon-iodine bond. That's the weak bond. So that would appear to be a reasonable place for us to be doing some radical chemistry. And indeed, that bond is 213 kilojoules per mole. So again, that's a weak bond. And under these conditions, we can make very nicely a new carbon-carbon bond and replace that carbon-iodine bond. Add our ester and replace the iodine in a conjugate addition. So 1, 2, 3 other carbons that come from the ester. Right, so that's a carbon-carbon bond formation using radical reactions chemistry. Okay, so we can also do other reactions. We can reduce weak bonds in the presence of other reducible systems. So this is an example from a classic synthesis of a prostaglandin. And we're going to make those sort of compounds. We've got a structure, we've got a lactone, we've got an ester, and we've got a CI bond. So as you know, you can reduce lactones, so that's reducible. You can reduce esters. Reducible. You'd use lithium aluminum hydride or something. Those reductions, those bonds, those carbon ions are strong bonds. The weak bond is the carbon iodine bond. And under these conditions, again, we'll meet them in some detail later on. We simply reduce out the carbon iodine bond and replace it with a CH bond. A very selective reduction of one particular bond. Which now becomes CH2 group. We'll look at that in some detail later on. And finally, really the best possible use of radical reactions for making rings. I mentioned last time that 5 method ring formation is very, very fast and very, very good, so-called rule of 5. And we can cyclize ring systems to make 5-membered rings. So again, if I number our starting material, always good to number your starting material if you want to find out or be sure where things are going. The weakest bond is the CBr bond. So that's probably the most likely place we're going to make a radical from. And indeed, under these conditions, we do. And we cyclize onto the double bond that's proximal to it. Make the primary ring. see some more evidence of that. Lots more in the third week. So a very nice way of making filamid rings. And the beauty of that reaction is we haven't got to block the OH group. If we're doing anionic chemistry, we'd have to protect that group. So the OH is free. CNs are also reactive functionalities. We haven't got to do anything with that. It supplies the reaction conditions very well. So we can do reactions with radicals to make quickly given ring sizes, and we haven't got to protect certain functional groups. So that's just a taster of some of the very nice reactions we can do with radical reactions. Okay, so hopefully you've all got the handout. And we're going to start now looking at, first of all, the structure of radicals. Hello. And then we're going to look at their stability and the reasons for their stability. And then next week we start to look at some reaction types. Now, you are all doing your degrees in Manchester. What does it always do in Manchester? Or supposedly do a lot of in Manchester?
Rain.
Ah, rain. So if it rains, what do we need?
Okay.
Water.
What do we need to protect ourselves? Umbrella. Right, there's an umbrella. Right, if you buy that from a particular shop in Manchester, which I won't name, they don't always work very well. So if it gets windy, what happens to it?
It inverts.
It inverts. So this is called umbrella inversion. That's the right way up. That's the wrong way up. And this is very useful when we're thinking about radical reactions, as you'll see in a minute. Right, so keep that in mind. Umbrella inversion. Very common effect in Manchester. So the structure of carbon-centered radicals. Right, we're concerned with these as reactive intermediates and as organic chemists, which are kind of founded on carbon. We want to use carbon-centered radicals mostly. So what is their structure? It's very important, their structure, in terms of stereochemical outcome of reactions. So let's remind ourselves about carbocations or carbeniamines. Carbeniamines are flat. So let's just look at a typical carbeniamine or carbocation, R3C+, trigonal planar. So we've got an empty p orbital. And there's a reason for this, and hopefully you'll remember this from Dr. Wallace in the first year. And the reason for these being planar is to do something called hyperconjugation. Let's think about the tertiary butyl cation, so trimethyl C+. What is hyperconjugation? Well, hyperconjugation is a stabilising effect between a sigma bond and an adjacent empty or half-filled orbital. Let's look at CH3 3 times C+. That's our empty orbital. In the adjacent carbon, we have CH bonds, sigma bonds. And when one of those CH bonds is in the same plane as the p orbital, we get a stabilising effect due to orbital overlap. So the hyperconjugation effect is due to orbital overlap between a sigma bond and an empty p orbital. Half-filled one. So we call that sigma to p overlap. That's a stabilising effect. Because the two electrons in the CH bonds can be delocalised into the adjacent empty orbital. I put a link on Blackboard, which gives you a very nice example of a crystal structure which shows the evidence of this. So that is why they're flat, to allow this coplanarity of the CH bonds and the P orbitals. The cations are flat. Carbanions are not. Carbanions are pyramidal. R3C minus is pyramidal. And we now have 2 electrons in nominally an sp3 orbital. But they are not rigid in geometry. They undergo the umbrella inversion. So those R groups are inverting continually, as is that lone pair of electrons. Just like an umbrella. So carbanions do not have a rigid geometry. And this is the same as ammonia. A classic example of umbrella inversion is ammonia. And that, of course, is isoelectronic. With a carbon. So ammonia does not sit rigidly as that. Trigonal pyramid is continually inverting rapidly with its umbrella. Right, so this is an important point. Cations, because cations are flat, carbanions are not. They have geometry, but they have rapidly inverting geometry. Right, radicals. Three possibilities. Rigid, flexible, planar. So again, a bit like a carbanion, that would be a rigid carbon centered radical. A flexible one would be like a carbanion. So we have umbrella inversion. And the alternative will be like a cation, which of course is flat. Okay. So, in general, apart from very few examples, they are indeed flexible pyramidal, just like carbanions, which means they haven't got a rigid geometry. This is important when we start to think about stereochemistry of reactions of organic radicals. Simple alkyl ones, they're flexible pyramidal, inverting very quickly in this umbrella fashion. Right, but that's only an alkyl one. What about allylic ones? Allylic ones are radicals which are adjacent to an alkene. So an allylic radical would be something of that nature. So it's a carbon-centered radical with 3 groups attached to it, but it is not flexible pyramidal because of that adjacent pi system. It is indeed trigonal planar because that allows our pi bonds. Radical centre is now trigonal planar, so that single electron can overlap and resonate with the pi system. So all those p orbitals are parallel, and that carbon this trigonal planar. Simple alkyls, amidal, allylic bonds, trigonal planar. Vinyl. Vinyl is more tricky. And that vinyl radical is one where the single electron is on an alkene carbon. That will be a vinyl radical. It's actually on the alkenic carbon. And there are two possibilities. That alkene. Pi bond in the plane of the paper. That single electron could be in a p orbital, which is at 90 degrees to the pi bond, in which case we'll call that R group is linear. That's a linear arrangement. Or it could be in a more sp2-like orbital, as in shown here. sp2 orbital. Again, at 90 degrees to the pi system, but now we have a trigonal planar rather than linear carbon. And this indeed is the correct structure of a vinyl radical, except it isn't rigid. Like the other ones, it's continually inverting. From front to back. I say these are very important concepts when it comes to discussing stereochemistry radical systems. Oops. Yeah. So they're continually inverting. Again, this is a very important point when it comes to understanding stereochem. Right, so those are things we really need to know when we start discussing reaction chemistry. Right, so the other part of this lecture is going to do a bit of maths. Maybe. We're going to look at the stability of free radicals. We know they're reactive, so they're not very stable, but we have a way of comparing their stability and assessing their relative stability. So how do we go about discussing, thinking about the stability of free radicals? And I'm not a physical chemist, but we're going to do some phys chem a bit. So when we talk about stability, there are two main sorts of stability. There's thermodynamic, as in how low in energy we are. What's the other sort of stability? Thank you. Kinetic, how quickly it reacts. If it doesn't react very quickly, it's kinetically stable. The most important one we're going to meet is the first one, thermodynamic stability. So, a lot of you will know I'm not very good at physical chemistry, but we're going to look at some bond dissociation energies. Let's just consider a bond dissociation. RH goes to R dot plus H dot. That is a dissociation of RH bond. Delta H flat is the bond dissociation energy. You've got to put energy in to break a bond, so that's going to be an endothermic process. Okay, so its value or magnitude is related to how stable R dot is. So the value of the BDE is affected by high stable and radical species on the right hand side. So we're thinking about radicals with short half-lives, 10 to the minus 3 seconds, and we can assess radical stability in a very crude fashion as radicals being either stabilised or destabilised, and we compare them at our 0 point with the methyl radical. This is a very important point. So we're going to compare given R dot with CH3 dot. And we define something called the stabilisation energy. ES is the stabilisation energy. And we simply define that as being the bond dissociation energy of methane, which will be quite large and endothermic, minus the bond dissociation energy of the radical precursor we're interested in. Very simple. So, if that value is greater than 0, i.e. the bond dissociation energy of methane is higher than the one of our component RH, then R dot is said to be stabilised. So if our bond dissociation energy is less than that of methane, R dot is stabilised. If it's less than 0, as in takes more energy to break RH than it does to break methane, then R dot is said to be destabilised. Destabilised. Very important, a very simple concept. Now on the next page, there's a very interesting table. Not to be learnt, please. So like pKa's, you should have a feel for relative bond strengths and certain trends therein. So I've got a whole load of different RHs here. And let's just subdivide them into little subgroups. So there's methane at the top, bond dissociation energy of 439 kilojoules per mole. Methane, ethane, 2-methylpropane, 2,2-dimethylpropane. So there's our first group, which I'm going to call alkyl, and we'll call that group A. Alkyl. As you see, the stabilisation energy goes up as you go from methane to 2,2-dimethyl. Next group is that lot plus that lot, then I'll put that one in the middle. And those CH bonds that are highlighted are all adjacent to conjugating substituents. So these are all B. So those CH bonds are adjacent to alkenes or benzenes or carbonyls. So adjacent to conjugating group. And again, those are all quite nice, big, positive stabilisation energies. Okay, so group C. I'm going to focus on the monohalo ones. Those top three have all got a quite small stabilisation energy, a little bit more stable than methyl, and those are the alpha halo ones. That's small. Group C. Okay. Now we've got a bit below, we've got an alkene and a phenyl. So that's what we call a vinyl and aryl system. That's group D. One of which is very bad, phenyl, and one of which is not very good, alkenyl. Group E are the oxy ones, where the OH bond is the one that's been broken. So those are oxy. E. And we've got adjacent to a heteroatom such as nitrogen or oxygen, so alpha heteroatom. Read that. So there are some trends in here, and that's what this is all about. And we're going to explain why those trends are what they are in a little while. So first of all, if you look at group A, alkyl, we go methane, ethane, isopropane, sorry, butane. And we increase in stabilisation energy. So for group A, what we can say, radical stability has a certain ordering for alkyls. We have methane, less stable than ethane, less stable than etc. etc. So CH3 dot is less stable than a primary radical, it's less stable than a secondary radical, it's less stable than a tertiary radical. This is the same as cation stability. Tertiary radicals are more stable than secondary, are more stable than primary. It's the first point from the data. If you look at B, we've got CH bonds adjacent to alkenes, or phenyl rings, or carbonyls, or nitro groups, and they all stabilise substantially. So adjacent conjugating groups are stabilising. And we'll discuss that again in a bit. Okay, halogens adjacent to our radical are only a tiny bit stabilising, so not much of an effect. That's group C. Alpha halo groups. Only slightly stabilising. Halo groups only slightly stabilising. Group D was the vinyl and the aryl or phenyl radical. Vinyl has a stabilisation energy of 4, so it is very different from methyl. Phenyl was minus 25, that's the least stable radical we meet. So group D is an important observation. Phenyl dot, very unstable. In fact, it's often called a hot radical. Again, I'll look at that in a minute. So a phenyl radical is not a happy beast. Adjacent nitrogens and oxygens, that's group E. OH bonds. Okay, methoxy radical is weakly stabilised. Phenoxy radical is very stabilised. So group E phenoxy dot is much more stable than methyl O dot. That's group E's observation. And group F is the fact that nitrogen and oxygen adjacent to the radical are very stabilising. Adjacent N or O is very stabilising. Like I say, I don't want people learning lists of bond association energies. There are some key trends which you need to be aware of and what the explanations for those trends are. Yeah, we'll look at this before we stop looking at it in a minute. So any radical that has a half-life of greater than 10 to the minus 3 seconds is what we call stable. It's not a very long time, but on radical terms that's quite stable. And indeed there are a few radicals that can be stored for months, years, without particular precautions, and again we'll meet some of these later on. But there's two examples of extremely stable radicals. One on the left always exists as it is drawn, or resonance form thereof, indefinitely stable even in air. One on the right is fairly stable in solution for several days. And the reason for that being is that we've got huge complicated systems which can help stabilise those radicals. Right, so with all that information, let's look at what factors are important in controlling the stability of our radical species. And the first thing we looked at was what I call group A, and that is the fact that tertiaries are more stable than secondaries, are more stable than primaries, are more stable than methyl. And this again is due to that wonderful effect called hyperconjugation. So this arises from electron delocalization between what we call the SOMO, the singly occupied orbital with the one electron in it, and the beta-CH bond. If you think about ethyl radical, which we know has got a bond, stabilization energy of 16 kJ per mole. So in essence, it's 16 kilojoules per mole, more stable than methyl, and that is purely down to hyperconjugation. So there's our radical, our CH2 dot. That's what we call the SOMO. And adjacent to it, we've got CH3. So again, just like we did with cation, we can have a CH bond in the same plane as our SOMO. When they're in the same plane, we get an overlap between the bonding orbital and our SOMO. Sigma to SOMO overlap. And this indeed has a stabilising effect, because there's 3 electrons there, 1 in the sigma bond, sorry, 2 in the sigma bond, 1 in the SOMO, and we can delocalise them essentially into new molecular orbitals. And we can draw a picture. There's our SOMO, 1 electron in it, single molecular orbital. There's my sigma, CH, sigma star, CH, 2 electrons. We mix these orbitals and generate some MOs. 3 electrons involved, 2 in that one, one in that one, and the overall effect is stabilising because we've gained twice that amount of energy, delta E1, and we've lost that amount of energy, delta E2. Overall stabilising. Delta E2 times 2 outweighs delta E1 1. So that's around 1, 2. So lowering times 2 is much better than high by 1. So that's the fundamental concept of hyperconjugation. And the more CH bonds or CC bonds we've got around that radical, the better it gets. So the secondary radical is more stable than the primary, and tertiary is more stable than secondary. Right, we'll just do the next section. So that's the alkyls. We said that in group B, conjugating substituents also stabilise. Well, that makes sense because we can delocalise and form resonance forms. Very important we get used to drawing resonance forms for radicals and get away from drawing double-headed arrows. So there's our LR radical. ES is 79 kilojoules per mole compared to methyl, simply because I can delocalise my single electron as so. Single-headed arrows, not double-headed, and that's because all those p orbitals are coplanar. And that's a big effect, 79 kilojoules per mole more stable than CH3, the effect of that alkene conjugation. Carbonyl group also has a good stabilising effect. Yes, it's not as good as the carbon-carbon double bond, 54. Again, that's simply because we can resonate our single electron in the same fashion. Resonance forms. The rule of thumb with resonance is that if you have identical resonance forms, it's a better stabilisation than non-identical resonance forms. Of course, the LR radical has two identical resonance forms, which will explain why we've got a better ES for the LR radical. Okay, and finally, phenoxy. You say it was much better than methoxy. Stabilisation energy of 75 kilojoules per mole. So even though we've got a much more conjugated system to stabilise that radical species, the stabilisation energy is only the same as allyl, and that of course is because the resonance forms disrupt the Arrhenius state. Etc. Okay, so there's two degenerate ones and one non-degenerate. Okay, so that explains phenoxy and conjugation with carbonyls, etc. But one that's difficult to understand and is really, really important in terms of getting a grip of drawing this, what causes problems, is when we have a heteroatom, like oxygen or nitrogen, next to the radical. It's very stabilising, 50 kilojoules per mole, methoxy radical. And this is conceptually hard to see. There's a typical radical with a heteroatom with a lone pair next to it. we can actually resonate one of those lone pair electrons and pair it up with that carbon radical. That is drawn like that. I'm taking one electron from my lone pair and sharing it with the single electron. That puts 2 electrons on carbon, and we lose one from X. That is a resonance form, so we can stabilise that radical by resonance. Of course, there is now some charge, plus on X and a minus on carbon. Very important you get to understand that picture. Show you in a sort of 3D fashion. There's my radical, there's my lone pair. All we're doing is taking one electron from the lone pair and pairing it with a single one. That's all I'm doing. Very important. And it's a very strong effect where X is oxygen or nitrogen. So if you look at the methoxymethyl radical, stabilisation energy 50 kilojoules per mole. And that is because we can share an electron, not in lone pair, with the CH2 dot. So very important. And that's a lot. You can do that resonance with fluorine and chlorine and bromine, but it's a lot less effective with halogens than it is with oxygen and nitrogen. Okay, we'll stop there because it's time for labs. However, I have some practice questions for you to look at.